My co-chair is Gary Barnhart. I want to say good morning to all of you, good afternoon, and good evening to those of us who are joining us online. Welcome to the 7th International Space Solar Power Student Competition, and welcome to the International Space Development Conference. The International Space Solar Power Student Competition is a global undergraduate and graduate level annual event presented by Space Canada in partnership with the International Astronautical Federation, the National Space Society, the IAF, Power Committee, and the Space Generation Advisory Council. This year, we're welcoming 11 semifinalists. We're very excited to see what these teams have in store for us, and so we'll jump right in. Before I introduce the competition manager, Dr. Andrew Wilson, who will be joining us online, I'd like to take a moment to tell you a little bit about Space Canada. Space Canada is dedicated to promoting, supporting, and encouraging international dialogue on space-based solar power through research, through education, and commercialization of technology. Space Canada accomplishes this mission by serving as a facilitator, enabling individuals, organizations, and governments to engage in the dialogue with the hopes of transforming the world view on this transformative technology. I'd like to send you the regards of George Dietrich, who's the president of Space Canada, who could not be here with us today. And with that, I will hand it off to Andrew, who's a graduate of the University of Strathclyde and is the competition manager for this year's competition. So, Andrew?
Yes, thank you, Haroon. I hope you can all hear me. My name is Dr. Andrew Wilson, and I'm the competition manager of the International Space Solar Power Student Competition. As Haroon has already said, this is a global undergraduate and graduate level annual event which is presented by Space Canada in partnership with the International Astronautical Federation, the National Space Society, and the Space Generation Advisory Council. This is the 7th year it has run, and the competition involves student teams coming together to address the sustainable and affordable space architecture and design of a space solar power concept as a form of renewable energy. This year, we received an exceptionally large number of high-quality abstracts, which has now been narrowed down to just 11 semi-finalist teams who will present to you today. Of these 11 teams, just 3 will be selected to advance to the finals at the 74th International Astronautical Congress in Baku, Azerbaijan, based on their initial project results presented as part of this conference. So it's with great pleasure that I present our semi-finalist teams. So please join me in wishing each team the best of luck, and I hope you enjoy their presentations. Thank you.
Presentation 1, you're muted. Please unmute. Presentation 1, are you able to hear me? Can you indicate?
Hi.
Great.
Thank you.
Thank you. All right. You have the floor.
Can いいか、始めていいかな。Hello everyone, I'm Kazuya Tsuyoshi from Kyoto University. I will show the presentation of the new power generation system via many low Earth orbit satellites. As background, SPS has advantages in sustainability. In general, SPS will use GEO and a large antenna to provide highly efficient wireless power transmission. However, the challenges of the previous SPSs are the limitation of receiving places, large structure, and difficulty of maintenance. To overcome these challenges, we propose a feasible system even in 2023. In the system, many compact satellites are used and placed in LEO, and the orbit enables us to transmit power to high latitude. We will introduce the detail of our proposed system. The system has three initial configurations: a 2 km square rectangular base, 50% of transmission efficiency, and 1 gigawatt of output DC power. Within this condition, we need to estimate one satellite transmitting gain, one satellite antenna architecture, total generation power with solar, and number of satellites. First, we show a calculation of the transmitting antenna gain from Swiss formula. Since receiving antenna aperture and transmission distance are fixed, the value from here, TX antenna gain becomes 55.94 dBi to satisfy the transmission efficiency of 50%. Second, the number of antenna elements per satellite is calculated. We get the value from this equation and using 8 dBi on the microstrip antenna. To realize the required TX antenna gain, 63,000 elements are needed. In this case, one dimension of the array antenna uses 251 elements. The size of the array antenna is decided to be 9 meters square. Third, power generation of solar cells is calculated. The size of solar cell is 20 meters square, and it generates 136 kilowatts at a conversion efficiency of 25%. The solar panels planned for use here are lightweight and flexible enough to be easily mounted on a rocket. With the current parameters, the weight would be 232 kilograms. Fourth, the desired number of satellites is calculated. You use the parameters written here. To realize the required power of 1 gigawatt on the ground, 27,000 satellites are used. With estimate results, we will confirm the calculations. First, one satellite transmitting gain 55.94 dBi. Second, one satellite antenna architecture square array is square array of 63,000 microstrip antenna. Third, generation power in solar cells is 136 kilowatts. Number of satellites is 27,000. This system using a large number of small satellites is similar to Starlink in the telecommunication field. Our proposed system is studied in small model and called distributed wireless power transfer. The right figure shows the overview of the experiment. TX antenna corresponds to satellites and RX antenna corresponds to rectangular base in our proposed system. The research confirmed that multiple TX antennas with synchronous operation improve transmission efficiency. A similar effect is expected in our proposed system when satellites are operated synchronously. Now, let's move on to the discussion of the cost. To estimate the cost, the mass of satellite is important. Satellites are composed of solar panel, microwave generator, antenna, and so on. For the parameter written here and using our calculated result, we have estimated that the total mass per satellite is 824 kilograms. We will calculate the cost of launch based on the satellite weight. The calculation assumes the use of the current available commercial launch vehicle, Falcon Heavy. The published launch cost is $9 million and the payload capacity is 63.8 tons. Since each of our satellites weighs 824 kilograms and 77 satellites can be launched in one launch. From these values, 351 launches are required at a cost of $31.6 billion. Based on the above, we estimate the total cost in the proposed SPS. The cost of satellite would be $27 billion when assuming $1 million per satellite. The cost of ground base would be $1 billion. The cost for launch is $31.6 billion as calculated in the last page. So the total cost would be $59.6 billion, which means $0.34 per kilowatt hour assuming 20 years of operation. Our proposed system has the following features. It is achievable with the technology of 2023. It is a feasible enough size. We use 2 kilometers square of receiving antenna and 27,000 small satellites. The satellites are placed in LEO. The cost is low compared to the previous study. Since our system can transmit energy when the relative position of the rectangular base and satellite change, the power can be transmitted to high latitude. Generated power on the ground is 1 gigawatt and the operation frequency is 5.8 gigahertz. Thank you for listening to our presentation.
You wouldn't have anything? Well, to get you, couple quick observations that you may want to check into. If you're going to do efficiency, calculations of power beaming, you need to learn about collection efficiency. Check the references in terms of IAC papers. You'll find out what's being talked about. You have to, anytime you're going to have an array, you have to figure out and explain how it is you're going to orchestrate it. Orbital mechanics is not forgiving. If you're talking about multiplexing beams, you're talking about making a phased array work. You can't wave hands and say that it's going to happen. You have to explain how it is that you're going to actually make it work. And if you're going to give specifications for a system, for a power system, you need to couch it in terms where you can match the specification to the context of the demand. Do we have any questions that we can? Tim?
Tim said 1 gigawatt on the ground. So if 50% efficiency rules, then that means we're transmitting 2 gigawatts, right?
Right. The answer is that's not what's shown in their math. Okay, so you've got, they need to fix that. And what I would like going forward with respect to each of these presentations is to give them some indication of how they can take their work to the next level. It wasn't, but that is absolutely, anytime you have a low Earth orbit situation, you have to, you need to address, shattering, as well as, orbit makeup. Can you address that presentation one? Oh, they can't.
Thank you. Yes, my question is, given that you're using a low Earth orbit constellation, you will either need to transfer power between satellites in space, or you will not have power available at nighttime due to shadowing from the Earth. I didn't see if your requirement for what you're trying to achieve is specialized power delivery or general power delivery, and I was interested in hearing how you guys are addressing the shadowing of the Earth during a low Earth orbit system.
Can you unmute? Are you able to unmute? Can you unmute?
Hello.
Yes.
Can you hear?
We can hear you now. Did you hear the question?
Yes. We are now thinking to place three receiving Rectina base, and the parts of satellites cannot receive solar power. However, and another parts of satellites can receive solar power, and they can transmit energy to parts of Rectina base. So multiple Rectina base, we will use multiple Rectina base, and we will transmit for the power, for the area that needs more power.
The specific question is looking at how do you account for the shadowing when you have something in low Earth orbit? It will not continuously be in the sun. There'll be significant shadowing. Okay. All right. Well, that's something you should address in your next your next iteration. Thank you very much. Do we have presentation 2 queued up? Okay, presentation 2. Please introduce yourself. You have the floor.
Could you hear me? Hi, could you hear me? We are Tanaka Lab students from Japan. So let's start our presentation. And we have prepared the video tape. So let's show it.
Thank you for your precious time. We are Tanaka Laboratory members. Now let's get started our presentation. Our project title is Moon and Mars Solar Power Satellite, SPS, in comparison to Earth SPS. In this slide, let me introduce us to you in short. Our laboratory is in ISAS, JAXA in Japan. Our main research subject is study of SPS structure WBT, discharge phenomena, and other subjects. Our members are from several universities, therefore, we have many backgrounds.
This video shows you the history of SPS development and the history of human space exploration. In 1968, SPS was proposed from P.E. Glaser. Tethered SPS was proposed in Japan over 15 years ago. Many R&D activities have been done. The latest technologies will be applied and the realization of commercial SPS. In recent years, we, human beings, really tried to colonize Moon and Mars, and some manned space development projects have launched. On Moon, Artemis mission is underway. This mission requires 10 kilowatts of power. On the other hand, on Mars, a migration plan has been proposed. In this way, in these colonies, stable electricity supply will be required. We think that SPS can be applied to these celestial bodies, and SPS will be a good candidate for energy supply system.
Next, we would like to explain about the purpose, goal, and step of our project. The purpose and goal of this project is to consider applying SPS to Moon and Mars based on SPS for Earth and clarify technical problems to realize SPS for Moon and Mars. Our steps toward goal are shown in the list. Step 1. Summarize the original concept of tethered SPS proposed over 15 years ago in Japan. Investigate environmental factors. We should understand the difference between us and others and figure out their characteristic future. Step 3. We will examine the orbit and the number of satellites, the amount of fuel for thruster. Step 4. Then, we will examine satellite size and calculate translation cost. Finally, step 5. We clarify technical problems of SPS on Moon and Mars with the difference to the tethered SPS. Our first step to understand conventional SPS model for Earth is important. This slide shows you the spec of tethered SPS. Our daily research is based on this model, and this model controls its balance using gravity gradient. We have to clarify how these parameter values were assumed before thinking about other celestial bodies.
Let's start with thinking about the difference between Earth and other celestial bodies. For example, when we consider the SPS around Earth, we have to consider the effect of atmosphere. When the radio waves through the atmosphere, it will be attenuated. So we have to choose the S or C frequency bands. That's because radio waves in that band are barely absorbed by the atmosphere. On the other hand, when we consider the SPS around the Moon, radio waves attenuation is rarely occurred because atmosphere doesn't exist on Moon. And future Moon landing site, Shackleton's crater, gives a constraints due to the terrain. When we think about operation in other celestial bodies, we must consider these environmental factors.
We'd like to explain about the orbit. On Earth, GEO is being considered as one of the operational orbits. In this orbit, power transmission is always possible because the antenna always points to the same place. And power generation is almost always possible because it is rarely in the shadow of Earth. On Moon, low lunar orbit is unstable due to irregular gravity fields. On the other hand, high lunar orbit is affected by Earth's gravity, and energy will be needed in south pole of Moon by Artemis Base Camp. To supply energy to it, we have to consider the suitable orbit, beam control, lieutenant, etc. On Mars, in Martian geostationary orbit, a satellite can always stay in the same place like Geo. However, Mars have more irregular gravity fields than Earth. To stay in the intended position, the thruster is used for orbital correction. In addition, Generally, the orbital altitude and the number of satellites is trade-off relationship. As altitude increases, power transmission time is longer and the number of satellites required is reduced. We will consider orbit based on previous studies and environmental factors.
If we could decide the orbit, we can also decide the size of satellite. Because the size of transfer antenna is mainly decided by distance between satellite and receiver site, size of them, and operating frequency. For example, Earth, we put satellite into GEO and use C or S band frequency. The size of satellite and antenna will be approximately several kilometers square. The sizes are estimated by these formulas. Then, how about other celestial bodies? For example, Moon doesn't have atmosphere, and there is no attenuation of microwave. So we can select operating frequency higher and make antenna smaller, as shown in this graph. If we decide the size, we can estimate the transportation cost. We can choose Martian geostationary orbit. The transmit antenna will be about 60 square meters on these requirements. The system will be very small and it seems suitable. However, there are many technical problems. For example, we know that the efficiency of power amplifier will decrease if we choose high frequency for operating band. Therefore, we will also examine to use other WPT technology such as high power laser. To clarify these technological problems and research the potential of other technologies are key to our final goal.
Now let's move on to our explanation of satellite transportation cost. This is an item that has a big impact on the cost aspect of this study. This table shows examples of rockets currently in operation or plans for operation. In this study, Starship is the main target because it can be launched at low cost. We would like to estimate the cost cutting of using ISRU via Moon and Mars. Finally, we will show you our future process and goals. The first step is summarize tethered SPS for Earth that are currently being researched and developed. The next step is investigate environment factors and orbits of Moon and Mars. Thirdly, we will consider Moon and Mars SPS realization. Finally, we would like to clarify technical problems to realize SPS for Moon and Mars based on SPS for Earth. Thank you for listening.
Okay. Questions? Yep. Can you get him the mic? Do we have the?
Hi. So you mentioned surface features such as the composition of the surface, the regolith, as well as the geography of the moon and Mars. I was wondering how that would affect the operation of an SPS system, and whether that entails anything more than the placement and the structure of the ground station. Does it affect the operation of the SPS in any other way?
Please unmute.
We think the effect of some kinds of regolith is not so much for the wireless power transformation, but we think about the construction about the lectern site. Maybe some kinds of effects occur, I think. So we have to consider it in future.
The couple things of note, you indicated your focus of your presentation is on the structure, and you did not talk about the structure. That would be something that you should address, both in terms of their, how you would visualize it being built. It would be different for those different venues. You spoke of the requirements in terms of the context, but you treated the initial foray of what's proposed as opposed to what is the actual requirement to perform something. There is a difference between the two, and your if you talk about the attenuation, there's actual models, and you need to understand the transparency of the different atmospheres. Okay, we hit the time limit on that one? Okay, for presentation 3, could you please come online?
My presentation. My name is Connor McRobbie, and I'll be presenting on behalf of my group, Dr. Jean-Pierre Hickey, Kyle McRobbie, and Jack Ellen from the University of Waterloo. And I'll be going over my presentation, leveraging the use of novel lunar in situ resource processing and in situ resource utilization methods with space-based solar power. So a quick background, kind of elaborating on the plenary this morning. Lunar in situ resource utilization and in situ resource processing are of high importance in today's research. As we saw this morning, there's a lot of people going into this now, a lot of government agencies and private companies. And they will be the fundamental building blocks to lunar infrastructure, as we're able to use resources from the moon rather than bringing material from Earth. This will help humans to travel to the moon and beyond. One drawback to a lot of these processes is that they require large amounts of power, and this is something that a lot of people are overlooking at this time. Space-based solar power is one possible solution for this, and it can be gathered and transferred to the lunar surface. This work covers a review of ISRU and ISRP methods that can be enabled by space-based solar power, as well as a novel method of material processing that is suitable and possibly even beneficial for scaling space-based solar power. This is a simplified roadmap to using resources in situ on the moon. First, the materials must be acquired. After this, they will be processed. And then the resulting byproducts will be used for a variety of applications. I'll be going into more details on these processes shortly, focusing on the latter two that require these large amounts of power. The overarching topic, however, being space-based solar power, can be used to generate these large amounts of power and transmit it to the lunar surface where these processes will take place. So the power requirement for ISRU and ISRP will all depend on scale. However, this is a known issue that takes a lot of power. We think space-based solar arrays will be ideal for capturing these large amounts of power and transferring that to the lunar surface via microwave or laser transmission, where a receiver will pick up this beam and convert this energy into usable electrical energy. So some of the ISRP methods, before any of them can take place, typically physical processing is critical. This could be refining the material, filtering as many of these processes benefit from small particle size. The first process is molten regolith electrolysis. This process melts the regolith, and then when the voltage is applied, it is able to separate the metal oxides into their usable metals and oxygen gas. This method has been proven on a small scale and could be scaled up further. Second method is vapor phase pyrolysis. Similarly, a very high energy process where the regolith is gasified under very high temperature. Following this, a controlled temperature environment would allow you to collect the species. Carbothermal methods use additives such as methane to reduce the metal oxides in regolith to gather oxygen as well as iron and silicon from the molten metal. And lastly, and likely the most common, is water electrolysis, where water would be taken from lunar ice, a voltage would be applied, and oxygen hydrogen would be produced. This method requires much pre-processing to move the ice to a plant where it can then be processed. A concept that we are proposing is an expansion on the molten regolith electrolysis method. We know that the decomposition of metal oxides is dependent on the electrolysis voltage, as seen in the table, and we're proposing to use a stepped voltage method to dissociate species in succession, as this would decrease the post-processing costs of the residual materials as the metals would be pre-separated. We will be designing mechanical concepts for this overarching topic, and we'll be performing small batch analysis supported by the Laboratory for Emerging Energy Research at the University of Waterloo. Similarly, in a vapor phase pyrolysis, a step temperature method could be used to gasify certain species of regolith to be collected in succession. So the importance of all these processes is how the materials will be applied. So oxygen is used everywhere. It will be used in life support, fuels, plants, water storage, propellant. Metals will be used in construction, infrastructure, and solid propellant. And silicon can be used for solar cells for future energy production. And this is where it all ties back to the space-based solar power, as all of these materials can be used to economically scale space-based solar power. The metals could be used as support structures in satellites. The silicon can be used in solar cells for energy production. And oxygen can be used as a fuel to get these in-situ resources into orbit. This creates a production cycle that makes lunar infrastructure more independent from Earth, as fewer materials need to be brought from Earth into orbit. And this space-based solar power can also directly support energy-intensive ISRU methods, such as additive manufacturing or casting, as these require high temperatures in order to shape and mold the material. So the main technological gaps are high technological readiness levels for technology in each aspect of the ISRU pipeline, from material acquisition to usage. A high-level system design that uses all of these aspects at reasonable cost, scale, and safety is required to realize this work as a whole. Lastly, potential methods for combining ISRT and ISRU methods could reduce the overall power requirement. As they are all high temperature processes, if you could move from a ISRT method that is of high temperature, not allowing the material to cool and using it directly, could save on a lot of energy. Next steps for us include a more detailed study on the solar array size for some of these ISRT and ISRU methods that I've gone over today. We will be developing a detailed design for the voltage step molten regolith electrolysis concept. And in the future, we will be performing lab feasibility studies with the Lear Lab at the University of Waterloo. So just a quick wrap up. Space-based solar power will be critical for future missions and settlements on the moon and beyond, as it can be a great source of power. ISRU and ISRP methods require a lot of power that can be generated through space-based solar power. I've shown a new ISRP method that can be more efficient at extracting metals just by reducing post-processing methods. And I show the importance of ISRU and ISRP to scaling space-based solar power economically by requiring less material from Earth. And lastly, technological gaps and next steps are outlined. Thank you, and I'd be happy to answer any questions.
Tim Cash, I have some questions. I did a study for Astrostron, which was a Greater Earth Lunar Power Station, and the assumption was the use of a 1,000-meter transmit antenna in lunar orbit and a 14-kilometer antenna on the surface, delivering something like, I'm going from memory, but something like 135 kilowatts base load, which was the assumption of a nominal or minimal lunar manufacturing process. And I noticed you called 20 kilowatts nominal or low. What do you consider the need of a manufacturing environment on the moon as far as a minimal or optimal base load power is concerned?
So the 20 kilowatt number that I use here is just small in a lab. To produce any large or reasonable amount of material would need a lot more than that. In terms of an actual number, I don't have one. I'm not entirely sure, but it would need to be much, much more than these sort of feasibility studies that have been shown.
Yeah, because long term, I've been assigned to look at nuclear reactors, and that's what, 25 megawatt. We're talking megawatts here, not kilowatts, folks. So anyway, that's sort of where it's going to head in short order on the moon. If we do start an industrial base there, it'll be megawatts for certain. Thank you.
Thanks.
Other questions?
I had a question, whether or not you guys have might have already passed, but have you guys applied or looked into a LEAP grant through CSA?
Not at this time, no. We're just in the sort of beginning phases of this project, but it's definitely something that we will be looking into.
Yeah, I think that the initial stuff has passed, but they might have more things going on. So I definitely look into that as a source of funding. So.
For sure. Thanks.
You're welcome.
And going through it, one of the interesting questions is you've identified a number of different methods in each of the areas with respect to ISRP, but relating it back to what the real requirements are going to be to make use of that would be a way to take it forward.
Sure.
Thank you very much. Appreciate it.
Thank you very much.
Okay, presentation group 4. Okay, stand by.
Will be virtual now.
We ready?
I believe so.
Group 4, presentation 4. You have the floor.
Hi. Hi everyone. I was told that we are taking a break for a few minutes. Hi. So we are a group of students, Team Solaris from Singapore, India, and Cameroon. We actually met just a few weeks ago to participate in this competition. So very excited to be here and to hear everyone's presentations. So I'm just going to quickly share my screen. Okay, can everyone see my screen? Okay, so today we're going to present on on-demand electricity for disaster relief drones in remote island communities, space solar power by integrating multi-port converters and lasers, and special thanks to our advisor who helped us at the last minute. So from Professor Rajivan from the Indian Institute of Space Science and Technology. So the problem statement that we have is remote island communities are especially vulnerable during natural disasters and have no reliable on-demand electricity to power emergency situations. And this is an issue because with worsening climate change increases the amount of natural disasters that are happening. And also the geographical location makes it difficult for these communities to receive emergency aid. And also, these communities usually rely on a single power source and physical infrastructure like telecommunication lines, or power grids, which are susceptible to damage. And this makes disaster relief missions difficult. So our proposal is a system that we are calling Solar On-Demand Laser-Based Assistance for Disaster Relief System, or Solaris. And while doing this, at the back of our mind, we were thinking more on the focus of what applications can space solar power be used for in the nearer term to justify the cost. And so the applications that we came up with was disaster relief drones for search and rescue, to deliver medical aid and food supplies, gather early intel about damage, and also to establish temporary communication networks. And so what we envision is an end-to-end wireless laser power transmission system for on-demand electricity using space solar power. So when disaster strikes, a control center and ground-based communication system is going to pick up that, it's going to send a signal to the solar power satellite. And what we hope to do is to have a diode pump laser transmitter that converts electricity from panels into a focused beam, and then uses face masks to split the beams to power drone charging ports, which are mounted with electric converters charging in specified charging zones. And then this will be used to, once the drones are activated, they'll be deployed to assist with the disaster areas. So our intended outcome is to reduce the human and financial cost of natural disasters, and especially since space-based solar satellite will cost approximately 16 billion US dollars. And so case study, perhaps, for example, Puerto Rico, when their power grid was destroyed by Hurricane Maria, they experienced a blackout of 11 months. It cost US $3.9 billion to restore electricity alone. Up to 3,000 lives were lost. And then it was also estimated that they required 132 billion US dollars in the longer term to repair damages. Yep. So now passing it on to Harry.
Hello, everyone. So firstly, our system will be comprised of a solar-powered satellite, which for a proof of concept, we try to design a satellite that will give us a required output of at least 1 kilowatts to power 2 drones simultaneously. And so we calculated the area of one solar panel of this solar power satellite to be 1131.2 meters square. And for this system, we'll have PV cells that are used in the solar power satellite solar panels that will have an efficiency of up to about 65% due to the gallium arsenide coating that will be discussed later in detail that we'll be using on the solar power satellite. And the solar power satellite will be launched at a geosynchronous orbit to achieve this efficiency. And so the next thing we would want to have is a diode pump alkali laser transmitter that we will have after converting from the electricity from the panels to a focused beam for Earth transmission. And so the satellite solar power beaming system will employ this diode pump alkali laser, which is a new kind of laser technology, although it was tested at about 2002 by the Lawrence Livermore National Laboratory. It has an efficiency of up to about 65%, so which is quite high. And so for lasers, it will make the satellite lighter and easier to deploy than microwave. And so for the laser, the third thing we would want to have is a face mask to split the beams as in the proposed architecture. And so we would use fused silica coating for this. And this is done so that we would have multiple loads that can be fed simultaneously. So we'll split a single beams, and so that the beams will be directed to multiple charging zones for the drones for disaster relief in case of an emergency. So the fourth point here is after directing the splitted beams, we would direct the beams to this dedicated charging zones due to environmental concerns. So we just want to have single point charging zones, but multiple zones, so that to be safe, to be on the safe side. And the technology we would use for this is a perpendicular configuration of mirrors that are used to direct to the target. I would want to use a closed loop control system for this, so not to have the lasers scattered in undesired directions. And so my team member will talk about the conversion of the
Hi
light
everyone.
to electricity.
Hello everyone. So on the drones, we are going to mount photovoltaic cells and converters. So for photovoltaic cells, we are going to use the vertical multi-junction type photovoltaic cell. And we are going to use thin film cells which are grown on gallium arsenide substrate, because as per a research by Fraunhofer ISC, we can increase the efficiency to about 68.9% using this. So we've approximated an efficiency of 65%. And also for optimal efficiency, we've chosen the laser beam of wavelength 858 nanometer. And as we know that the light energy, which does not get converted into electricity, will get converted to heat energy. So the heat management system plays an important role here. So we are using phase change material for cooling, and to be more specific, we are applying paraffin wax on the cells for cooling them. Next, the electricity from the photovoltaic cells, they will be fed into multi-port converters. Multi-port converters will obviously be compact, and also for the processing efficiency of multi-port converters, we've taken it to be approximately 80%. However, the efficiency can be increased to about 90% if we modulate the switching frequencies. Next, the electricity from the multi-port converter will be fed to a drone charging port, which will power the drones. So the drone charging ports are lightweight, and we've taken a rating of about 65 kilowatt DC for the drone charging port. Next, these are the technical details of our concept. For the proof of concept, we've just considered powering 2 drones simultaneously for disaster management. So if one drone charging port has a rating of 65 watt DC, then for 2 loads, we are taking it to be 130 watt DC. So taking the processing efficiency of our multi-port converter as 80%, of our PV cells as around 65%, the power which we require from the solar power satellite is around 1 kilowatt. And taking 1 kilowatt power from the solar power satellite, the area of one solar panel is approximately 1131.2 meters square. And since the drone charging port requires very small amount of power, this technology we can use it in future to take more power from a solar power station, and also to power some other loads, some other critical loads such as electric vehicles or medical facilities or ventilators in ambulances. But for them, since these loads require AC power, we would require inverters for them. Now, these are the next steps which we could think of. Like for phase 1, the technology demonstration for Solaris, for cost reduction, what we've planned is that instead of launching a separate solar power satellite, we are going to fit additional solar power or additional solar panels on the last stage of the rocket, so that instead of the last stage, instead of burning out, we can convert it automatically to a solar power satellite. For example, like some potential collaborators like ISRO, they've offered from the last mission, they have offered that we can use the last stage of the rocket for free experiments. So we could just use it to make a solar power satellite. And the phase 2 would be launching of a geo satellite, that we can increase the size of our solar panels to power more number of drones. And also we can establish multiple drone charging sites. So this is our team Solaris. We are a diverse team from 3 different countries who are very passionate about solar power, and we had teamed up to somehow help the community using solar power and all of our specific interests like electrical engineering, space engineering, how we could combine everything and somehow benefit the community. So thank you everyone. You can always reach out to us on the email ID given on the screen, and any questions then please feel free to ask. Thank you.
And doubts as to whether they can really get that much power out of it. And they need to do some testing in the field, I think.
Yeah, a constructive suggestion is actually providing both an end-to-end and a piecewise efficiency table, because that number number looks like it's just a perhaps wishful thinking. You had one more back there.
How good does the aim on the laser have to be in order to reach the drones or the charging port, and how do you plan to reach that precision?
Okay, can you take yourself off mute and try that question? Can you take yourself off mute and answer the question?
Did
You're
you hear the
still on mute.
question?
You're still on mute.
Yeah, sorry. I think you got cut off there a little bit. You didn't get to hear the feedback.
Yeah, we couldn't hear anything. It was disconnected for some time, I think.
You want to ask it again,
Yeah.
please? I think you were asking about the accuracy of the laser being able to hit the drone.
Yeah, how accurate does the laser have to be, and how do you plan on having that precision on your system?
So we were actually inspired by there was a already existing optics powered drone that was doing it with quite high precision. I can get back to you on the specific details.
Okay. Also, if you can go through and include a comparison of the scale of your system versus the scale of need, it would make it a lot clearer, because it's not, apparent as to whether or not this is an exercise in overkill or not, or underkill. Okay.
Hi, I had a question about your transmission wavelength, and correct me if I'm wrong, but is it on the order of nanometers? And I think I saw 858 nanometers. And if it is, could you speak on the risks of transmission using such a high frequency and therefore high energy beam?
Yeah, because of the risks of the transmission, we are planning to have dedicated charging zones for the drones. So the lasers will be transmitted only to those specific zones, and those zones will be prohibited for any human or any life entry.
Yeah, also the drones don't have to go all the way towards the ground.
Yeah.
So it might not, the idea is not to reach the level where it can accidentally hit a human being. Yeah.
Yeah.
Hello, I was really impressed with the end result, kind of seeing where this could go. I was curious about how you were handling cloud cover and things like that, atmospheric problems.
Yeah, because of the atmospheric problems, we've taken that 60% of attenuation of the lasers will exist. But even after that, if we increase the size of our panels, of our solar panels of the solar power satellite, then we are getting a high amount of power, which even doesn't matter if it's getting attenuated.
Thank you very much. Can we queue up presentation 5?
Okay, am I audible? Can everyone hear me? Am I audible? Can everyone hear me? Okay, great. Yes, thank you. All right. From vanquishing the thirst of energy of small cities and nations to powering up ideas globally, the search for reliable energy and green energy has been on an uprise since the 90s. The search for greener and more reliable energy has led us here into harnessing energy from the biggest star in our solar system, the sun. So, ladies and gentlemen, I'm Hassan, myself, and my friend Ushan Sakuntar. We are here to present a novel modular structure to increase the efficiency of solar panels in space-based satellite systems. So when we talk about SBSP, or rather space-based solar power, it is the concept of harnessing electricity out of solar energy from outer space to the use in Earth. This has been on research since the very early 1970s. And when we talk about the comparison of what this brings in, we have already ground-based solar panels, and then now we have this extended to space. When we look at the difference is the rate of production in solar energy. When we talk about producing solar energy in Earth, obviously we need to consider the atmosphere we live in, which creates a great distortion for the solar rays to reach our Earth and then get produced into electrical energy. All these atmospheric distortions and factors are eliminated out in space. And when we consider the higher collection rate, longer collection period, all these things, and lack of atmosphere in outer space, we can produce more solar energy out there in space compared to ground here in Earth. This is our general conceptual design. It is based on very simple concept here. As you can see, the power out in solar space is harnessed, the solar energy is harnessed, and it is transferred into RF energy using microwaves, and it's transmitted to Earth. From Earth, we can use ground receivers or microwave antennas to receive this energy and then use it to our plans according to here. So this is our general conceptual design. And then there's a technical issue. There are basically two types of implementing this. That would be, the first one would be of transmitting using reflectors. As you can see here, the concentration type designs mention the use of reflectors here. So what we basically do here is use these reflective surfaces, as you can see, which would reflect the solar rays, concentrate them on the solar panels in outer space, and harness more energy. It increases the production of energy, electrical energy, and then we transmit that back to Earth. The second method would be of not using these reflectors, just using solar panels directed to where the sun is, and then just harness the power out of it and transmit to Earth. Here the images from 1 to 4 would show us the different types of concentration. These are some of the designs that these reflectors can be implemented in different shapes, in different modules, and in different parts. So when we talk about these reflectors, what is the main problem that we come across? To harness large amounts of energy in kilowatts, let it be in megawatts, to power up a huge city, maybe a nation, maybe in gigawatts, if we are talking of future, the bigger thing, the first thing that comes into our mind is the space. We have to build huge infrastructures out in space to harness powers in kilowatts and in megawatts. So that is the biggest problem that we encounter right at the moment. By using these reflectors, what we can do is we can launch out in partitions or small components. So to counter this huge issue, we have based a solution right here in this presentation. Another issue that we have to face is while using reflectors, the traditional method of reflecting, effectively reflecting, would be use of mirrors, where mirrors are just plain structures where they could reflect light and they are not flexible, or they cannot be broken into very small pieces, which would reduce down the efficiency. So the solution that we propose to overcome the main problem that I mentioned on our previous slide is this novel structural design that concentrates solar energy. As you can see, this is a reflective surface in a conical shape, which is attached to the base, where the base would have solar panels, and the rays would be reflected directly onto the solar panels using this conical shape. When we look at the build material here, it would be it's a mirror fabric, which is very flexible, and it could be folded or then retracted as according to our plans. And then as we can see, it is extendable with these structures here. So this can be implemented to reduce the space that we are talking about. So this is the simple design. As you can see, this design would reflect these solar rays right down to the base of the solar panel, and the concentration of these rays might cause a lot of heat as well. There's a high chance of creating a lot of heat. So as an added advantage, what we can do is we can use thermoelectric generators at the base of the solar panels to produce some more electricity, which would come in handy at some point, and it would give us an added advantage on the system as well. Also, in this design, when we talk about general solar panels, there is a glass layer on top which protects the solar panels from other harmful atmospheric distortions back down in Earth. We can actually eliminate that glass pane here when we go to outer space, which would also increase the efficiency by a slight amount, which is really good. And we can use that. Instead of that glass panel, we can use a collimating lens as well to increase the efficiency of production here. This slide would show a live action video of how this conical shape would retract and expand. It was a video there, but due to some technical issues, it's not getting played at the moment. But anyways, this conical shape would be folded at the very start. While on deployment, as from the command, we can retract it, and it will come into a conical shape as such, and then it will go into action. So when loading and in transportation, we can keep it contracted. Hence, we can bring up more space in travel and reduce the travel cost. And thus, we can eliminate some of the travel costs, and we can pack in more modules of these reflectors and panels and send it out to space and deploy them and expand them as our wish. We can send this as one big unit or in smaller modules as well. So the material that that I mentioned earlier, that was about the reflective fabric, the mirror fabric. We can either use the Mylar reflective sheet or the silver mirror fabric. These two sheets, Mylar reflective and silver mirror fabric, have been in space industry for a long time. It's been there and it's been used for other space researchers and other projects as well. So it's nothing new. We could use this off the market itself, and these sheets are very effective. And to conclude, in summary, the problem was transporting large reflectors out to space and then constructing a huge unit out there to harness more electrical power. And the solution that we provided here was a novel solar concentration structural design based on cone shape that can be implemented in space very easily. So I hope this project is a good one, and it could slightly increase the efficiency of all the production out in SPESP. And thank you for listening to us.
Do you have any questions? Rod, you had a question, right? Okay.
Any others?
Did I see that correctly? When the Mylar or whichever material you use, you can push that out and in to focus. Is that a continuous change that would happen? And if it is, how will you overcome the maintenance of that piece falling apart with moving parts?
Yeah, Mylar sheets have already been in space for a long time. So they are using space applications. Since it is flexible and it can be replaceable, we can replace these Mylar sheets in a time. Like if it is degraded, we can replace that one easily. So this structure can be implemented as a modular wise. So the replacement will be done in easily. So the other one is silver mirrored fabric, but this is not used in space before, as we know. So this would be also a great solution if we do study.
One of the challenges you face there, if you're going to claim that you're going to be collimating the beam, you're going to need to know what sense and measure you're collimating, and have the ability to the control electronics and the optics to be able to do that, which you don't address. You did go through and indicate that your methods are to increase the efficiency. Your calculations are based on a fixed insulation on Earth. There is no fixed insulation on Earth. It's highly variable unless you're hanging out in southern Arizona or Saudi Arabia. You indicated your main problem is launch costs. That's something you may want to certainly revisit in terms of establishing your context. And it's not clear your use of a musical glyph, what that's supposed to convey.
Yeah, the graphic images that we were trying to use here was to show how this conical shaped design would contract and retract. That was one thing. And the other one showed how the are reflectors used to power transfer to Earth.
It's the danger, having engineers view something, they take it literally. All right, thank you very much.
Thank you so much.
Presentation 6. Presentation 6, can you queue up, please?
Good morning, dear esteemed judges and fellow participants. I am Shreya Yadav, here to present along with my teammates, Sakshi Mishra. Thank you for giving us this opportunity to present our innovative idea on the feasibility of origami-based solar panels for wireless power transfer, incorporating methods to mitigate harsh space environment.
SPSP stands for Space-Based Solar Panel, which is a concept that involves capturing solar energy in a space and transmitting it back to Earth. It used as a clean and sustainable source of power. The basic idea is to place large solar power satellites in low Earth orbit around the Earth, where they can continuously receive sunlight without being obstructed by Earth's atmosphere or weather condition. SBSP generates electricity without producing greenhouse gas emission or air pollutants, minimize the need of the extensive land use.
But there are various challenges faced by SPSP that are limited space availability on spacecraft and satellites, weight constraints for launch and deployment, need for efficient power generation to meet energy demands, harsh space environment, and flexibility and adaptability to changing conditions.
The flow of working begins with the deployment of origami solar panels. These panels are stored compactly during the launch and then unfold in space to maximize the solar energy capture. The solar cells generate DC electricity power conditioning, converting the DC electricity into desired voltage and frequency. To transmit electric energy generated by the solar panels to the Earth, a wireless power transfer mechanism is employed. The WPT system consists of transmitting unit on board the spacecraft and receiving unit located on Earth.
Origami. The ancient art of paper folding has fascinated cultures around the world for centuries. It allows us to transform a simple sheet of paper into intricate three-dimensional structures. This art has inspired us to reimagine solar panels by incorporating fold patterns that enhance their functionality and efficiency. Our self-designed origami solar panels offer a transformative solution to the challenges faced by the traditional solar panel installation. With their flexibility and portability, these panels pave the way for a more sustainable and accessible future for renewable energy. Here is a preliminary design of the origami solar panels along with its fold patterns made on paper. We are continuously exploring new ways to design our solar panels and make it more compact and efficient.
Advantages of origami solar panels are efficient. These are efficient power generation with high efficiency solar cells, optimal space utilization due to the folding and unfolding of the solar panels, lightweight and reducing overall weight of the SDSP system for the efficient launch and deployment. Now, what it seems like having origami solar panels with the fold ratio of 4 times the initial folded size. Along with the integration of self-healing perovskite solar cells, these offer several advantages: compact storage and deployment. Origami solar panels allows the efficient storage and transportation due to their ability to fold it into a compact form. Increase surface area. When unfolded, the origami solar panels provide a significant larger surface area compared to the folded state. This increase the surface areas allows for the greater exposure.
We are using perovskite solar cells because of its lightweight properties, making them highly suitable for space application, where weight reduction is crucial. Perovskite solar cells are also known for its self-healing capability. It adds a unique advantage to the origami solar panels. Self-healing properties enable the solar cells to repair any minor damages or defects they may encounter, such as small cracks or scratches. This enhances the durability and lifespan of the solar panels. Along with this, they have a demonstrated high power conversion efficiency, rivaling traditional solar cell technologies. By utilizing perovskite solar cells, you can benefit from their efficiency to maximize generation from available sunlight.
The low Earth orbit of the Earth contains various energetic charged particles which consist of electrons, protons, and ions. These particles are mostly generated by solar particle events and galactic cosmic rays and are trapped by the Earth's magnetosphere. The space environment in the Earth LEO can be harsh and challenging due to these factors. The proton pose potential risks and challenges for space-based systems and mission. High-energy protons can penetrate the solar panels and can damage to electronics, which leads to decrease in lifetime and efficiency of the solar panels. Our mission focuses on inner belt proton clearance rather than electrons from outer radiation belts, since protons are 2000 times heavier than electrons. It can do more damage to our SDSP system than an electron. We are using superconducting DC rotating coil to generate a strong magnetic field. By rotating this coil, we are generating the rotating magnetic field around the spacecraft. When this field combines with high energy protons, the proton experiences a fold called Lorentz force, which acts perpendicular to the proton velocity, resulting in their deflection and redirecting it away from resulting it away from the spacecraft. We are using superconducting materials for rotating coil because it reduces power loss and enables the generation and stronger magnetic field.
Now, coming to the electromagnetic ion cyclotron waves. Imagine you have a bunch of charged particles floating around in a magnetic field. These particles naturally want to move in circular paths around the magnetic field line, just like a ball tied to a string. So if we give a little push to some of these ions, which can happen because of the particles that are coming from the sun, they start to move fast. And when these fast moving ions interact with magnetic field, they can create waves. It's like the fast moving ions are having a chat with the magnetic field, and they make waves as they talk. These waves are called electromagnetic ion cyclotron waves because they happen when the ions in the magnetic field interact at a specific frequency. Think of it as a special type of conversation that happens when the ions and the magnetic field resonate with each other. These waves can do interesting things. They can scatter and accelerate particles like electrons, making them move faster or change their directions. They can this can This scattering can help these particles escape from certain areas in space. We are using EMIC waves in addition to the DC rotating coil, as it's not enough to precipitate all the types of electrons with all its frequency. Combining the EMIC waves with DC rotating coil is an effective approach for removing the high energy protons from low Earth orbit.
Electromagnetic interference is a disturbance caused by electromagnetic radiation from various sources that can interfere with the proper functioning of electronic devices or system. Electromagnetic interference compliance plays a crucial role in WPT in an SBSP system by using EMIC techniques, which refers a set of practices and measures implemented to ensure compliance with EMI standards and regulations. Some of the techniques are shielding, filtering, and grounding.
By incorporating EMI compliance measures, the SPSP system can minimize the risk of electronic interference. This ensures that the operation of the DC rotating coil and origami solar panels is not disrupted by unwanted electromagnetic signals. EMI compliance ensures that the WPT system operates without interference from electromagnetic signals emitted by other devices or systems. It minimizes the risk of signal degradation or disrupt during power transmission.
The advantages are lightweight structure, safe operation in harsh environments, compact storage with origami solar panels, and EMI compliant transmitter highlight the immense potential of space-based solar power. These advantages contribute to the cost effectiveness, reliability, and efficiency of the system, bringing us closer to the harnessing solar energy on a larger scale. Without ongoing advancements and research, SPSP holds the promising of transforming the way we meet our energy needs while paving the way for a sustainable and greener future.
While the advantages of SPSP are promising, it is crucial to address the consideration and challenges associated with the technology. By developing robust maintenance and repair procedures, optimizing the unfolding mechanism of origami solar panels, and carefully managing cost and scaling strategies, and these challenges can be overcome. With thorough planning and continuous advancement, SBSP has the potential to revolutionize our energy landscape and provide sustainable, clean energy for the future.
Limitless potential of SBSP has captivated the imaginations of scientists, engineers, and dreamers alike. With the technical feasibility established, our sights are now set on scaling up the revolutionary technology to capture and transmit substantial amount of solar energy. In doing so, we aim to create a cleaner, more sustainable future while mitigating the harsh space environment and making SBSP commercially viable. Get ready to embark on a journey that will take us beyond the boundaries of traditional power generation.
These are the references served as a valuable sources of information, guidance, and inspiration for our project. We thank you all for listening to us so patiently. If there are any questions, we are happy to answer.
Let's get the microphone set. Questions? Tim?
I congratulate you on your idea for the EMIC-enabled devices, but that's one of my fields of expertise, electromagnetics, and I can tell you from my experience that there isn't any aerospace company I know of that would use such a extremely high TRL device to protect things unless they had an extreme TRL lowering program to make them safe and lower and high reliability every time. It's just not going to happen. So if you can somehow do that and make such a device able to provide a stable source, my hat's off to you, but I don't know how to do it, and that's what I do for a living. Thank you.
Other questions?
Thank you so much.
So I had a question about the solar panel origami folding that you mentioned. I think you talked a little bit about the mechanical difficulties and how it's obviously, since it involves more folds, it's going to be more mechanically intricate than a traditional fold. Do you think the benefits of it being more compact outweigh the costs of having such a mechanically intricate mechanism?
Yes, particularly for this project, I believe that it is very important. It is very important to use origami solar panels because we are talking about large scale development of this project, because large surface area of the solar panels can generate more electric power. So the main problem is launching and making it more compact so that it can be possible for us to expand it to a larger scale. So for this project, I think origami solar panels are perfectly the most important type of concept that we must try to incorporate it.
Great. You went to some effort to explain the problem space by presenting a flow diagram, but you offered no characterization, either qualitative or quantitative, with respect to that diagram, nor did you show how the stuff that you were talking about fits into that diagram. And in particular, when you're talking about something that radically alters the folding factor of solar cells, shouldn't you be quoting the numbers that explain how good your mousetrap is at achieving the objective that you set out? When you're talking about reactions to radiation, there's very interesting work as to what extent radiation is a problem that is endemic as you try and increase your efficiency, or is it something that is more specific to the molecular resonance frequencies? There's some very neat work you can look into there. Okay, thank you all very much. In terms of when you're talking about radiation, the coronal mass ejection is a more common term that's used to describe that. They used a different one, on their chart.
They use SPE. What does that
It's rather than using SPE, I'd recommend you use coronal mass ejections. That's more common. Okay.
Barry, how many teams do we have left? Because
we have, that's 6. We've got, 11 total. Okay. All right. So heading on to number 7. They're virtual?
In person.
In person.
These are our friends right here.
Great. Presentation 7, you have the floor.
All right.
Okay. All right. Welcome everyone to our presentation. We are Texas SPS, and our presentation is the analytical cost optimization of orbital parameters and propulsion solutions for SPS in LEO. And so it's a bit of who we are. We are from the University of Texas at Austin, and that's a little while away. And our team consists of me, I'm Abdul Bari Agbola.
I'm Peyton Burlington.
I'm Mark Dunn.
And our faculty advisor is Professor Adam Noakes. And so a little bit of an overview. We will have our introduction, which we just did. Then we'll go into the problem and mission, then the cost optimized orbit that we've done, and then also the propulsion system, and then we'll conclude with the references and questions. So our problem and mission. So despite like the large amount of heritage that we've done, including like researching the Hallmark NASA SPS Alpha, we noticed there is not a lot of data on performance parameters for S orbital elements such as like altitude, inclination, attenuation, and those are really necessary for us to, I guess, characterize a spacecraft in LEO. So, if we have the spacecraft too low, it'll be affected by drag. If too high attenuation, there's a lot of space loss given a single attenuation. And also since a lot of these parameters are closely related to propulsion parameters, we plan to have that as a topic of interest. So our mission objective, we plan to identify the feasibility of a LEO, low Earth orbiting satellite by hypothesizing the most economical attitude, eccentricity, inclination, and propulsion systems subject to several non-deterministic physical models such as density and drag.
So now we'll go into the cost optimized orbit analysis that we did. So we took in, it's a multivariable problem with trade-offs between several different input physical models. And so those models include spacecraft heating, density, gas dynamic drag, atmospheric attenuation, and space loss. And so we took those into our analysis, and then we quantified them in the economic sense, and output that as a function of altitude to find the cost optimized altitude for a LEO SPS. So in order to do this analysis, we had to make some assumptions. So all of our assumptions are listed here. Some of them are that we're assuming a circular orbit, a 5-year mission lifetime. We're looking at a single module of the SPS system with 5 square meter frontal area. And then assuming a Falcon 9 launch vehicle for cost estimates, a cost per kilowatt of 20 cents USD, which is a worldwide average. And then a spacecraft coding of Z93.
Yes. So driving this multivariable analysis are many physical models, mostly modeling the non-deterministic processes governing the density and the temperature in the upper atmosphere. We started off with our first iteration was an analytical model on the left, which related density to the altitude exponentially. Later, we found out that this was not very accurate due to mostly solar activity affecting the concentration of molecular or atomic oxygen in the upper atmosphere. So we moved on to our second iteration, which was based on empirical data of the number density of atomic oxygen in the upper atmosphere, which, as you can see, is closely correlated, the first and second graphs here on the right, closely correlated to solar activity. So once we obtain a relationship between drag or between density and altitude, we could use that data to find out a relationship between drag and altitude, which ultimately, the higher the drag, the more requirement for thrust. So the higher requirement, basically the propulsion system is going to be heavier. There's going to be more propellant. The walls of the propellant tank are going to have to be thicker, and the overall cost of the mission goes up. So that's the downside of having a very low altitude orbit. The upside is that the attenuation of the transmission frequency is less because the transmission distance between transmitter and receiver is reduced. And here we have calculations showing how we calculate the required mass of the propulsion system as a function of altitude. So the results are here on the left. We have the results based on the relatively inaccurate analytical model, the exponential model that we used first. And the second iteration is at 400 kilometers, which we later discovered to be about the optimal altitude for the kind of system that we're discussing. And you can see the results of a Monte Carlo analysis relating the drag, the different values of drag to the probability of occurrence.
So as Mark mentioned, the next physical model that we looked at was atmospheric attenuation and space loss. And so this benefits from a lower altitude. And so on the right, you can see we plotted atmospheric attenuation and space loss from 0 to 100 gigahertz for the transmission frequency, as well as 100 to 1,000 kilometers for the altitude for the orbit. And there's a very large spike around 60 gigahertz due to the oxygen effects in the atmosphere. And so we zoomed in on the left side of that graph, which can be seen in the figure on the right. So just looking at 0 to 50 gigahertz. And from this, we can see there's a minimum as you get lower in altitude, as well as you approach 50 gigahertz in frequency. So we used all these physical models that we've discussed and plugged it into our analysis and quantified it in economic loss, which can be seen by the graph there. And so there's this exponential decay reaching a minimum and then a gradual increase after that point in altitude. And that minimum occurs at 354.4 kilometers. So that would be the cost optimal altitude for a SPS LEO orbit.
As you can see from the last figure, being slightly above the optimal altitude, where the minimum of this curve drives the costs up much less than being slightly below that altitude. So we can afford to be a little bit above it. And that's actually what we decided to do in order to achieve sufficiently short repeat periods for repeating ground tracks. So we increased the optimal altitude from about 365 kilometers to 404 kilometers, which would allow us to have about a 2-day repeat period for the satellite to pass over the same ground stations in a repeating manner. So that's the equation on the bottom. Then on the top, we have an equation that's related to the inclination. It's describing the precession of the longitude of the ascending node, which is the highest order orbital perturbation term due to the oblateness of the Earth. If we pick an inclination of about 63 degrees, we can minimize this effect. And this inclination is close to the latitude of our chosen launch site, which is the Pacific Spaceport Complex, which has a latitude of about 57 degrees. So the delta V required for this inclination changes is not high. And so the resulting orbit looks like this. These are the ground tracks along with other orbital plots. And as you can see, the ground tracks cover many high latitude communities in Canada, which are off of the electrical grid and could potentially benefit from wireless power transfer with space-based solar power. And as you can see, the optimal altitude is 404 kilometers. We've assumed a circular orbit to avoid accounting for the circularization of the orbit due to atmospheric drag. And the repeat period of 2 days is a consequence of that chosen altitude.
And so for the propulsion system that we characterized for our orbit, we created a database of around like 40 different engines of different test readiness levels. And we found that electric engines are the most optimal for our uses. And so we created a weighted decision matrix where we valued thrust to power, system weight, and ISP, and had ISP as, I guess, the most heavily weighted, since that would incur the least amount of cost to orbit insertion. And so I guess the top three engines were, I guess, the LISA Pathfinder, the NSTAR, and the PPS 1350, which I guess can potentially be used on a LEO satellite. And I guess fast forward, we would use, I guess we would try to characterize air-breathing engines as well as include more variables in our calculations to achieve like a more precise conclusion. But that is it for us. These are our references. Anybody has any questions?
Good morning. I was curious about, well, it's sort of a question and a comment on two different things. First off, the question, I forgot my question. I'll come back to that. The comment was that this looks like a good approach for optimizing altitude for a single satellite, but I think the real cost would be for the entire constellation, right? So at a higher altitude, you would be able to have a larger coverage area, again, going to the difference between LEO, GEO, MEO, and those ranges. So that would reduce the number of satellites you would actually need, which might be a factor in actual total cost for a constellation, right? So I think that that might be something to look at extending into if you get a chance to, or if another team's going to do a similar thing. It'd be good to look at taking this model and integrating it into an entire constellation where you optimize for cost of the constellation rather than cost of the satellite. And the other question, now that I remember it, is, again, I'm curious about how you address shadowing during this time and about power availability. Are you looking for constant power availability to these communities or periodic availability? And I don't believe I saw, were you guys using laser or were you looking at microwave? I didn't notice if that was in there. It was
microwaves.
It was microwave, right?
Yes.
Okay, cool. Then we can skip on that question. Yeah, I'd like to know about how you deal with shadowing, since it sounds like you're going to be in a LEO regime where you have to deal with that more. Thank you.
I can take it. Yeah. So it's definitely going to be periodic coverage of different areas. The customers are up to, they're not specified, but high latitude communities in Canada are a good option. The repeat period is 2 days, and we've accounted for sort of the eclipsed periods of the orbit. They're not too, I believe they're on the order of 30 minutes per orbit, so they're not too bad. And we are looking for direct transmission of power as it's being received, direct transmission to the ground station. So trying to minimize the use of batteries in order to minimize weight.
We're going to cut into lunchtime by 15 minutes, so we're going to go to 12:15, but that means we also have 3 teams to go yet, so we're going to cut the questioning. Sorry. You can find these guys around. Hit 'em up.
Yep. And you should, check your data with respect to atmospheric attenuation. It's wrong between 90 and 100 gigahertz. You use a sparse data set.
Okay.
Find the right ones.
Thank you.
Okay, we're now heading for presentation 8. Will be virtual.
Hello, hello.
We can hear you.
All right, good to know. So my name is Neil Sorkin. I'm here from the University of Maryland, and I'm talking to you guys about laser-powered jumpers for low-cost, high-coverage swarm Martian exploration. So let's look at how we're looking at Mars today. Perseverance rover gets high-quality data with multiple sensors on board, and I would consider it a high-cost single rover. And it has limited coverage. In its time on Mars, it's covered about 18.62 kilometers as of yesterday. And that comes out to 22.7 meters per Earth day. On board the rover, there's a META sensor, which has a suite of sub-sensors, which measure air temperature, humidity, pressure, radiation, and thermal radiation. But if we look back at the map, what about the data over here in the bottom left or in the upper right? We don't know what's going on over there. Thus, if we have engineered jumpers, we can collect low-cost, high-quantity data with some permissible attrition rate. This avoids the whole terrain navigation problem, and it can shake off dust by jumping. Alternatively, we can use magnets to repel the dust. I should say that it jumps by retracting this string using a high gear ratio motor, and it flexes these carbon fiber bows, and it can release all that energy at once. It has these small batteries inside the nose cone to slowly build up the energy. Now, looking at one example of a sensor, or looking at the META sensor suite, we can collect the same data on these jumpers. For example, air temperature, humidity, pressure, radiation, and thermal radiation. And on the right, you see a HumiCap sensor, which is measuring relative humidity. And this is a very small sensor coming in at 45 grams. So these jumpers are actually self-righting, and you can steerably launch them. And the battery size is fairly small, 0.388 watt hours. And it gets you about 10 jumps fully charged and about 56 meters per jump. Thus, with only 10 jumps, laser power beaming. So if we have an orbiting transmitter, you're going to have a telescope architecture pointing a big laser and not necessarily trying to hit the target fully. Just because that battery is so small, we can afford some large losses. Kind of think of it as, catching one drop of water in the shower. You have the whole shower water coming down. You only need a little bit if you're charging such a small battery. The attenuation by wavelength, I could not find so clearly as it is on Earth. Sure, Gary might have a resource for that. Dust particles are known to be an issue here. And I know that we're going to need a high power level laser for this. There's going to need to be some pointing system, most likely a 2-axis gimbal for this transmitting. And we have to have a battery for when it's in eclipse in its orbit. The receiver would be positioned in the nose cone, and the nose cone itself could be a receiver for solar energy directly. And it's because that's made of silicon, it's transparent to IR. So if we have an IR laser, we can pass that through. So we have redundancy in case something goes wrong with the IR transmitter in orbit. We have a backup system so that these jumpers can still operate, perhaps at a lower jump rate or less coverage. But the mission isn't over if one of these fails, or if even the transmitter fails. So also the winding string preserves progress. So if it's compressed some amount, and then it has to wait for the orbiting satellite to come overhead, that's okay. It can compress again and wait for it to make another pass, compress again, and repeat the process. And it would be best to recharge when it's self-righted, just because it's more facing the proper way compared to if it's on its side. It might not be an exposed cell, and the idea is to put it in the nose cone in some way. And we're going to trickle charge this very slowly over time. No need to burn the components, melt it. And then using an electromagnet to repel the dust is going to be helpful in this case. So in conclusion, I've presented a novel high coverage solution to get large data amounts without a single point of failure. And this is actually a pretty low power use case for space-based solar power. So if there's any questions, I'd like to take them.
There's an interesting paper from IAC on the
Can you restart the question? I missed the front of that.
Oh, there was, yeah, there's an interesting paper from IAC on the use of graphite structures as batteries, which could be an interesting correlation to the structure you proposed there. We are running short on time. Could we have group 9 come forward? Okay, you have the floor.
Hi everyone, my name's Megan, and I've just completed my undergraduate degree, in which I done a dissertation which is titled An Investigation on the Challenges and Opportunities of Space-Based Solar Power and its Potential in Aid in the UK to Achieve Net Zero, which is what I'll talk more about today. So currently in the UK, there's an ongoing energy crisis and the prices have just skyrocketed. The UK still uses a lot of fossil fuels and still buys in a lot of its energy. So it's predicted by the UK government that by 2035, electricity demand will increase around 40 to 60% compared to the current demand. So this is kind of where space-based solar power can come in to offer a renewable form of energy. So my research project, I critically analysed the National Space Strategy, the British Energy Security Strategy, as well as the Net Zero Strategy. So there was no mention of space-based solar power in the British Energy Security Strategy, and the space sector as a whole was not included in the Net Zero Strategy. As well as this, there is no legally binding documents on the sustainable use of outer space, so it just kind of shows there's a clear gap. So the UK's pathway to net zero. The net zero strategy was created in 2021, and as previously mentioned, the space sector was not included in this. So the main aim of the strategy is to reach net zero gas emissions by 2050. So space-based solar power can help with this as it's a renewable form of energy, so it can help move away from the use of fossil fuels. So within my literature review, I looked at the economic and technical feasibility of space-based solar power. So in regards to the economic feasibility, initial investments from government would be necessary to fund space-based solar power. And the UK could benefit economically from exporting this energy through wireless power transmission to different countries. And this was just a quote that was in the Net Zero Strategy, which the government stated that while there are significant costs in reaching net zero, the cost of inaction is much higher. So this just kind of shows that it will probably get to a point where the system won't really have to be economically feasible because the world just needs the baseload energy that it can supply regardless of the cost. So in regards to technical feasibility, there is a large amount of land required for the development of the Rectenna. However, a study did show that it will take up less land than what a wind farm would use because wind turbines will have to be continuously developed to keep up with the rising demand for energy, whereas the Rectenna will just stay situated in that one area. And wireless power transmission, although demonstrations have been conducted, larger ones are required at scale to prove its efficiency. So just the importance of eco-design. Shanoin defined eco-design as a preventive approach to mitigate the environmental impacts of a product, good or service as early as possible in the design phase. So the image that I've included there is just kind of outlines the method of life cycle assessment, which is quite an effective use of eco-design. So as you can see, it kind of shows you from design right through to the disposal. So environmental impacts will be quantified at each phase of the life cycle. And this can help with impact categories such as ozone depletion and global warming. So this, for like space-based solar power, this should be carried out at each mission phase to really quantify the environmental impacts. So to find out more on these topics, I carried out semi-structured interviews with 6 stakeholders within the space-based solar power industry. So these are split up into 3 different themes, which were net zero, economic and technical, and eco-design. So what I found in regards to the net zero strategy was 83% of participants believe net zero is important to achieve. I also found that 50% of participants believed space-based solar power can act as an enabler in achieving net zero, though the other 50% believes that it possibly can. So this just kind of shows there's a little bit of doubt amongst professionals, amongst the capabilities of space-based solar power. But this was in regards to the challenges of space-based solar power. So they believe that if these challenges can be overcome, then it can help with net zero. So this was a SWOT analysis I created based off of the responses from the stakeholders on the technical challenges and opportunities of space-based solar power. So I'll just mention the main, like the ones that came up the most. So the main technical opportunity was found to be wireless power transmission, because everyone knows it can work, the physics of it are understood, and it can be used to export energy to other countries. However, as it hasn't been tested at a large enough scale yet, that's why it is also a challenge. But another really big challenge found was robotics, because they are needed for in-orbit assembly and manufacture of space-based solar power. However, these currently do not exist, so that's why they are quite a big challenge. So this is another SWOT analysis on the economic challenges and opportunities of space-based solar power. So the biggest opportunity was found to be that the energy sector and the space sector will merge together, which has never happened before. So this will create a new industry, which will offer new jobs, create new skills, and offer new capabilities. And one of the biggest challenges is the large upfront costs, because the space-based solar power system is so large that it just makes getting investment quite difficult. So then, in regards to the effectiveness of eco-design, there were various methods of undertaking eco-design that were identified. So each stakeholder gave a different response. So, for example, one of them said carbon footprint assessment, another said life cycle assessment. So it just kind of shows there isn't one best way of undertaking eco-design. And every participant believed eco-design can reduce the environmental impacts of space-based solar power. So that just kind of reinforces its importance to make space-based solar power as sustainable as it can be. So this was a table on the challenges and opportunities of eco-design that was also found from undertaking the interviews. And as you can see, there are a lot more opportunities that were found compared to the challenges. However, the main challenge was found to be trying to get companies to see it as an important issue. So as mentioned earlier, there's a lack of legally binding documents. So that means the space industry has just been allowed to use whatever materials they want and things like that, without really having to think about the environmental impacts. So that makes it hard to incorporate into the design of systems. And for opportunities of eco-design, for the first time, you're able to quantify and actively reduce your carbon footprint. So eco-design gives you a transparent design, which can help to avoid greenwashing and reduce environmental impacts through life. But this can also help with gaining funding because it will prove that your system is sustainable and environmentally friendly. So just to conclude, despite space-based solar power's potential, it is not included in any UK policy. And space-based solar power could help the UK move away from fossil fuels, which will help achieve the net zero goal of net zero gas emissions by 2050 by being a renewable baseload form of energy. And just for recommendations for academia, research findings should be directed towards ministers and government. And for industry, professionals should be provided with eco-design training and should begin to apply eco-design to all developments to make their system as environmentally friendly as possible. So thank you for listening.
Time for a question.
Just a comment.
Yeah.
I thought that was excellent as far as the social implications of technology. That was spot on.
Yeah, in terms of the social implications of technology, that's clearly a reasonable treatment that they've got there. Interestingly enough, the UK Space Agency's Space Solar Power Initiative was not mentioned. Is there a reason for that? Did you
I think
understand?
I did mention it in my actual report, but just didn't think to mention it in the presentation.
Okay. All right. We've got the next in-person presentation. Thank you very much.
Thank you.
Oh, well, I already got it. Oh, okay.
Perspective.
Can I get confirmation that the audience can hear me?
Yep, sound good.
Good morning, judges and esteemed guests. I'm Turner Bunbury, and I'm joined by my peers Ishan Sarkar and Rufino Pereira. Today, we are going to be presenting on a trade analysis on the transmission efficiency and feasibility for wireless power transmission in space solar power mission applications. Here is an overview of our presentation. The purpose of our presentation can be broken down into 3 distinct categories. First, we would like to conduct trade analyses on the attenuation losses using the antenna characteristics from commercial antennas that we have found. Additionally, we would like to provide experimental proof of concept for conversion from transmitter beam energy into electrical energy by using USC's ground station infrastructure. And lastly, we'd like to generate a detailed cost estimate of end-to-end energy concepts for power generation, energy storage, and wireless power transmission from harnessed solar energy. Going on into our literature review, one of the first scientific concepts that we wanted to uncover was atmospheric attenuation. As you can see in the figure on the right by Fingus and Brown, scattering losses increase sharply with the transmission frequency. So we determined that the best transmission bands for energy transmission were the S-band, X-band, infrared band, visible band, and UV band. As can be seen, power transmission outside of these bands is unfeasible because the majority of the beam energy will be lost due to atmospheric attenuation. The next portion of our literature review focused on wireless transmission efficiencies. Although there hasn't been as many studies from space to ground wireless transmission, we were able to find a lot of numerical analysis of spacecraft to spacecraft transmission. One group, led by Gavin and Tapucci in 2017, determined a method for determining the transfer efficiency between spacecraft using microwave radiation. They developed this non-dimensional transmission parameter, which they then used to calculate the transmission efficiency. As can be seen in the plot on the right, the transmission efficiency increases logistically with this transmission parameter. We hope to use this transmission parameter as a point of comparison in our future studies. And lastly, we want to compare our current mission. Compare current missions to our mission. So our mission analysis focused on spacecraft to spacecraft energy transmissions because these are shorter distances and have less energy attenuation. We found one group that was using CubeSats to perform a technology demonstration of wireless power transmission. As can be seen on the graph on the right, their mission consisted of 2 separate CubeSats, a transmitter unit and a receiver unit. And they've been able to demonstrate in their lab a total transmission efficiency of around 43% using microwave radiation. Moving on to our trade analysis, one of the first things we wanted to determine was what would be the optimal orbit for our wireless power transmission. We considered 2 orbits, low Earth orbit and geostationary orbit. As you can see, low Earth orbit has a much smaller transmission coverage, but lower space attenuation due to the decreased distance between the spacecraft and the ground stations. On the other hand, the geostationary orbit has higher transmission coverage, but a much higher space attenuation. We decided to go with low Earth orbit because the space attenuation was so great that the low Earth orbit's decrease in transmission coverage is made up by its increase in space attenuation. For our low Earth orbit, we chose a sun-synchronous orbit so that the satellite would have constant illumination to the sun to recharge its solar panels. Our orbit is at a 97.5 degree inclination and will be at a 600 kilometer altitude. The next trade analysis we decided to conduct was on the directional gain of the antennas. To determine the optimal directional gain, we considered over 6 different types of antennas. As you can see, the space attenuation and receiver gain was the same for all of these antenna types, but the directional gain directly affected both the transmission gain and the power received ratio. The antennas in this table are sorted from worst to best. The best antenna that we found was the patch antenna due to its high directional gain, which culminated in a negative 8.8 decibel power transmission ratio, or roughly a 13.2% power transmission efficiency. I will now be passing on this presentation to Ishan.
So now we wanted to create an experiment that does a proof of concept of changing a transmitter's beam energy into electrical energy by using the USC's S-band and UHF antennas. The purpose is to demonstrate feasibility and technology and get real-world efficiency estimates. On the left is the S-band, and on the right is the UHF band. Next slide. So here's a brief overview of telecom operations at USC. So you have the azimuth and elevation rotors that just controls roll and pitch of the antenna and connects to a passband filter between 2.2 and 2.3. You can change that filter to whatever range between like 2.4 and 2.8. We just wanted to look in that range. Then we connect to a low noise amplifier because it's in Los Angeles, so there's a lot of ambient noise. So we want to reduce the amount of noise as possible and amplify the signal, which then connects to a 3 dB splitter. So then we can look at different portions of the filter within a bandwidth. And that connected to an internal spectrum analyzer on our computer, which we use the software SDR Sharp. And then on our desktop computer, we use the software Orbitron to predict when the satellites will pass over USC and PSD rotator to automatically move the antennas. Next slide. So here is an example of NOAA 18 that we tracked, which is a climate change, climate observing satellite. We saw the downlink frequency of 2.25 gigahertz, S-band with SNR 7.5 dB with peak at negative 98.7 dBFS. On the left, you can see the initial acquisition angle, signal acquisition, and then on the right, you can see the signal phasing to the left as time goes on since the satellite's moving over. Next slide.
And so the next thing that we wanted to do, we're going to create a link budget, so that way we could compare the theoretical versus the actual atmospheric attenuation. And so we took the frequency and then we were able to calculate the weight. Next slide, please. And so based on the link budget, this is the analysis that we found. And so we found that we were able to determine a size of 4 meters. Next slide, please.
So additional considerations, like in our abstract, we want to look at attenuations, specifically atmospheric attenuation, so atmospheric contribution from the antenna microwave components, zenith atmospheric attenuation, effective cosmic background noise, CMD noise temperature. So we put that all into our total noise density Excel sheet, and we put that into our final link budget analysis. Next slide. So we wanted to verify our assumptions, or verify our link budget using SDK. So here are our assumptions. On the left, we calculated the gain in noise floor of our antennas, and on the right, we calculated the G over T ratio. Next slide. And then we got an SDK link budget. On the very right, EB over NO, that's our signal to noise ratio. We got around 7.8, which is what we acquired through the S-band antenna. And our bit error rate is within standard rates of 10 to the negative 5 to 10 to the negative 8. Next slide. And here's just a summary of all the satellites we tracked. You'll see at the bottom is just proof of signals that we captured in the phasing.
And so another trade that we did was we wanted to investigate solar cell efficiencies. And so we found the most efficient 32.2 was from Spectrolab, and it's XESF space solar cells. Next slide, please. And so then in order to account for eclipse times, it's also important to be able to have secondhand batteries. And so this is just a list of batteries that we found that fit with the spacecraft bus of 32 volts. Next slide, please. And so another important thing that we wanted to do was generate a cost estimation. And so there's four approaches. And so the first one is a cost by analogy, which is basically from Heritage. And so that's so we could compare apples to apples. The next one is parametric, or cost estimating relationships. And that's expressed as mass per dollar, and grassroots. And that's basically the most high fidelity estimation, because it's taking actual estimates and building a database. And so the fourth one is a hybrid, which is a combination, and which is actually what is usually typically done for to have a cost, an accurate cost estimation. Next slide. And so this is an example of what we plan to build, and as a cost estimation. And
yeah, and so this is just an example from an Earth to Mars mission of looking at phase A to phase Z, and our goal is to reduce the telecom architecture costs by increasing the efficiency rate, so we can reduce the amount of hardware you have to bring up into space. Next slide. So this is power generation. We're looking at different modes of future work for launch, cruise, and nominal and eclipse. This is what we want to do in the future and graph out all the power generation. Next slide. So final future work, we want to design a laser-based WT experiment because that's where the future is heading. We know there's space policy issues against like aviation, like birds, and like when satellites get in the way. We want to create a high-fidelity MATLAB to automate the process, and we want to create a power analysis for each mode, including ellipse. And also look at thermal, because thermal couples with power. With bad thermal regulation, you have bad power degradation. Next slide. Conclusions, we just did our trade results, show proof of concept of the USC satellites, and create link budgets. Next slide. And here are references. Are there any questions?
Okay. All right, since we're running so late, we'll go to the last team, 11.
Yeah.
I think there's a lot of, yeah, it's charging. I think it's loading. Are you leaving?
I'm going to vamp real quick while they're working on the technical. Hi, I'm Sean. I had a couple of just general thoughts for all of the presentations that I figured I would offer. Now, number one, for folks that are remote, if you have the chance to record, make the recording because it can help avoid all sorts of other issues. You get a chance to go through it multiple times. Good to go? Oh, you want me to move over here? There we go. All right. And for everybody, when you're doing a comparison or an analysis, try to make sure that you're comparing apples to apples, and then offer what that thing that you're offering, in this case, space solar power, is in comparison to. Just saying, oh, there's problems in the world and this is a solution, cool, but there's other solutions that may not involve space solar power. So if you're going to put, for example, nuclear completely out of consideration for some reason, state, we took nuclear out of consideration. We acknowledge that that is a way to do power on the moon or on Mars or wherever else. And as much as possible, try to give a breakdown of the comparison of what the thing it is you're comparing it to, even if it's not necessarily going to, space solar power may be better, it may be worse, but that will help understand what the thing is that you're actually comparing it to. Yes, sir.
Now, all of the presentations will be available to look at for the next few weeks. I mean, I was late for.
Yes, I'm getting nods saying yes.
What's the deadline?
The plan is to make them accessible. I'll go through and work with Space Canada to make that happen. Historically, that has been the case. But the Space Solar Power Symposia is not running this term. The initial round of comments, we'd like to, have what we can while we're here. We're going to have to go over the timeline that Space Canada wants to, impose on this. But this is, an ongoing process, and part of, I think, our negotiation objective is to give each one of the teams a place to go with this. There's, this isn't just a static, effort, or at least we certainly don't want it to be. We want them to be able to take the work forward. And being able to make resources available to support that is helpful. Also, what was being mentioned about comparisons, oftentimes you don't have you may not be in a position to go and do an elaborate brief of all the other things that you're not talking about, but what you can do is for what you are talking about, what is the key or fundamental figures of merit that matter? Okay, and that certainly can make a difference.
For those of us that are providing feedback, can you tell us what the prompt was that they're responding to?
Room. The specific articulation of the prompt. There is out on the website. It's typically there. Did it get posted this time? The prompt that the teams responded to.
So, Gary, even if we're a few weeks late in responding,
Yeah, what I can go off and do in these regards is I can make the commitment that any of the notes that are pulled together and turned in, we'll do the best to make them available to all the teams through some kind of wiki or other mechanism that we've I know the guy that has the equipment to throw at it, so I think I could. That, while it's fresh in your mind, absolutely. Okay, the reality of the situation is that there's a subsequent to that when you have the presentations at your disposal that represents a next level.
Haruno's back a little bit, and I brought this up, but one thing that I think would be useful to have in this competition is sort of a bit of a focus on funding. Like, how is this going to be funded, right? Whether or not it's initial government grants for the initial science research, and then maybe starting to think about, angel investors or venture capitalists, so that some of these students could maybe launch this into a career, a startup that could actually make this happen. Because if it don't make money, then it don't make sense. So.
Well, the United States is falling behind other countries and showing some initiative, and it's very striking. The fact that the United States and its citizens generated this back in the 70s, and Gary and his community have furthered this, but our political leadership has fallen short in providing the incentive and funding and authorization. It's very disturbing as an American citizen. Thank you.
So I think this is important to, sort of educate the public on this as a potential solution for net zero. Right?
What if I connect to my email
Were you good?
and I open it on the drive because I have it on the drive? Do you think it's the same? Or?
NSS, through the Alliance for Space Development, has been talking about this topic as recently as March and continuing with folks on the Hill. So NSS and Space Frontier Foundation, all the folks in the Alliance for Space Development are pushing on this right now.
And this afternoon at 3:30, masquerading in the Space Ambassador session, there is a talk on space solar power, what's the latest news, which will prove, seeing as how I know the guy that's giving the presentation, it will prove interesting. Okay. This is in the Space Ambassador session at 3:30. It's a talk on space solar power, what's the latest news in Terabang. If you are familiar with today, if you're familiar with that peculiar punctuation mark. So there's, there interestingly enough, there are things going on around the world. Curiously, though, most of the folks that are working on them, for one reason or another, are not in a position to talk about it. Which is why there isn't a Space Solar Power Symposium, co-located with a conference this year. Instead, we had to find somebody that could address the issues at hand without running afoul of the various and sundrious, complications. I'm going to do my best to do that. And, not that I'm particularly good at tap dancing, I'm going to endeavor to ensure that I offer as straight an answer as I possibly can to, any questions raised in those regards. It's in the Space Ambassadors track. I haven't gotten my program book yet, so I don't know what. Frisco 5. So that's here.
Try again.
I'm going to see if I can hornswoggle that to happen, given that the equipment's already in the room.
We can see them in there. So tell them at the bottom, there's share button.
Okay.
I'm going to get Isaac.
Oh, okay.
For them follow the prompts.
Yeah. They're connected? You're connected? Okay. Can you share the screen?
Yeah, we just shared the screen now. You can see?
Yes.
Okay, let's do it.
Okay, thank you everyone, and sorry for the time. Good afternoon, ladies and gentlemen. We are Team 40N for the Moon from Issy-sur-Pairo. We are settled in France, and today I'm very excited to present you our project DAL, or DALE. We are a group of students, very dedicated, and yeah, we are very excited to show you what we're working on. Right now, I'm gonna bring you to a trip to the moon, where we intend to bring new solutions to the space in a sustainable way, and to revolutionize the moon infrastructures. So we know that by 2040, PwC estimates that around 1,000 astronauts will be settled on the moon. And we also know that nowadays, to send 1 kilogram of material to the moon costs approximately 300,000 euros by the best launcher available. So there's a need to use these in situ resource utilization. So humans, they need to breathe, they need energy, they need lighting, they need heating, they need infrastructures, they need roads, houses, places to live. All of these things can be solved with the solution that I will show you today. So next slide, please. Our project focuses on the infrastructure problem. And next slide. This is the solution. This is a solar sinter, which is a technology concept that allows to focus the solar beam into a specific point on the lunar surface. But the question is, how will this be powered? Heliostat satellites. Our ambitious mission consists on sending 12 of those in the orbit of the moon, in the same orbit. And these heliostat satellites will be able to power the ground heliostat or solar sinters, and they will be in this single orbit. So our project consists of two different assets. We have on the moon, we want to bring Rego bricks, and then on the ground, on Earth, we want to build ecological construction sun. And both of these are tackled with our own solution that we're showing you today. I'm going to talk about it a bit more in the next slide. Okay, so here you can see a CAD design of what we intend to do. This is the ground setup, the heliostat on the ground for the Earth and for the moon, and the dimensions and the heat point and power needed that we estimated that will be required. Here you can see the heliostat, which will point the solar beam into a specific point to melt the regolith. And then the regolith, once is sintered, because what we want to do first is to change the shape and the size, it will go through a conveyor arm and will be sent to a crusher. And then from this crusher, we will model the regolith in different shapes that will provide the reusable needs. So we will get the shapes that we need for building infrastructures, for building tables, walls, everything. Next slide, please. So here are some numbers that we've estimated. So first, we know that more or less to bring a solar sinter to the moon will cost around 150 million euros. And the selling price of our bricks will be around 1,000 euros per brick, with a capacity production of 1 brick per hour, which means around 9,000 bricks per year. And some of the key features of this technology will be the modularity and the adaptability, which will allow us to reuse them for several applications. But the most important thing is actually the energy-free production, which comes in place thanks to solar power. So how is this possible? This is thanks to this crater on the moon, which provides constant sunlight. But we know that, of course, some of the solar sinters won't be positioned in this specific place because they will be all around the moon. And this will be solved thanks to the heliostat satellites that I presented you before. So if they're in this mode, it will be great. But if not, we have the other solution of the heliostat satellites. Guys, are you there? Oh, no. Yes, it's not the best day today.
Yes, we are here.
Okay, because we cannot see the slides.
Okay, we see it.
I don't know, maybe it's our internet. I'm not sure. I think it's our internet.
Apologize for that technical.
Oh yeah, it's phasing out now.
Are we out?
Connected. Okay.
Actually, on the YouTube channel, we can see that we are transmitting on the direct.
Yeah, but that's another source, I think.
Okay.
Same computer.
Got it. All right.
Okay, we can continue. So there are several applications for the Rego bricks that we intend to build. We have, as I mentioned before, we have tables, chairs, walls, infrastructure to save all the mechanical things that they will need when they're settled there. Next, please. Okay, and here we can see some numbers for the Earth asset. So the solar center on the Earth costs approximately 300,000 euros, and the selling price is around 0.1 euros per kilogram, with a capacity production of 0.1 meters squared per hour. How many bricks per hour is that per day? Do you remember, guys?
What?
How many bricks per hour was that? We calculated it. I don't remember exactly. I don't have my notes.
So it's zero. It's 1/3 of tons of sand per day.
Okay.
It's in kilograms of sand, not in bricks.
Okay. So, and also an important fact is that this will be 40% compliant with the ESG. Next slide, please. Okay, so now to bring you into perspective why we choose the Earth asset, not only the Moon one, which will bring us to the Moon, in fact. We know that, next slide, please. We know that the water on the Earth is the first thing that we are using, and it's the highest demand. But you know what the second? The second is sand. Next, please. Which is very similar to regolith. We know that worldwide we use 50 billion tons of sand per year, which means 18 kilograms per person per day and around 7 tons per person per year. Here you can see the pyramid of Giza to scale. And then you see next to it, we see what China used of cement in 2000, from 2006 to 2016. And then the US in the past 115 years, which is a lot. Next slide, please. We also note that due to this higher demand of sand, there are ecological disasters like river sinking, coastal erosion. We have destruction of habitats. We also know that there are some social disasters, such as the one in India in 2022, because of the mafias that have the power to use all this money and all these weapons. There were like 193 people died, which included some young people also. Next slide, please. But why is desert sand not used for concrete production? Next one. Well, we know that construction sand is sharp, has different shape and different sizes, and it's bigger than the desert sand. So we need a process in order to make this desert sand available for construction. And all of this can be achieved next slide, please, thanks to the solar center. But in order to bring you a feasible solution, first, we're going to bring you some plan that we have. So because we are from France, we are very lucky to have 2 solar centers next to us. So the first one is used for research, and the second one is owned by a private person, which was the first one built on the Earth. And as French students, we had the chance to visit it. We visited the solar center. We talked to Denis Edelin, which is an expert on this. He's spent all his life trying to build a solar center that was useful. This is our team here on the right, you can see. And it was an amazing experience because we got to see how this process is achieved on Earth. And then we thought about the idea of bringing it to the Moon. Next slide, please. So here you can see some samples that we use. Here we see some sintered sand, which is suited for construction. This was implemented in a solar center from desert sand, and then we produced this sintered. And then here you can also see a regolith simulant, and then the real bricks from this simulant. I couldn't bring this because I was flying from France, and I didn't want in the plane any problems to come here, but we actually have them physically. Next slide, please. Okay, and here you can see also like how similar, but also how different these sintered Sahara desert are in comparison with the construction sand, and why we need these experiments, and why we need to test and make sure that this actually works. Next slide. Next slide. Okay, so here's some business analysis. So we intend to first bring the Earth asset into play. So that means doing all the research, having the CAD designs and everything, and prototyping, and then calibrating it and testing. Once we have this, we intend to gain experience first on Earth and revenue in order to move to the moon by 2024. And then build everything that we try to do, like the moon landing, and then commercialize it. Next slide, please. This is a price analysis that we did. We contracted with a company in Australia to know more or less the price that we would need in order to get some revenue from the Earth. And this was approximately €95 per ton bag. So this is in comparison with, guys, can you tell more about this slide? Because I forgot now the exact numbers.
So yeah, actually, we contacted an Australian supplier because they supply NEOM or the line project. The price is €95 for 1 ton. So we try to align on that price for the sand sintering. So our target price is to be this price or even cheaper. But let's see how it goes.
That's a pretty impressive CAGR number in the economy we're in now.
Okay, next slide, please. And here you can see that we intend to make money from 2030 onwards. So this is a process, and it takes time to actually make some revenue out of this mission. This is the value chain. It's a long process that my team, in fact, Lalo, maybe you can explain it because he's the finance person in this team. So now that you're online, maybe you can help me with this part.
So yeah, let's speak about the value chain. We want to incorporate ourselves into the brick production, but we will go into the value chain of the lunar economy because we don't want to excavate the regolith. Actually, we want to find some supplier, like maybe Rasor from NASA, to get the regolith, buy the regolith from them, and to put it into our device into the solar sinter in order to process it and make it something valuable, and then to sell it to national agency or startup or private actors present at this time, maybe in 2030, 2035. So this is how we go in the value chain.
Okay, next slide. So to summarize a bit, what we intend to do is we want to use solar power to bring into play these solar sinters that will focus on 2 different assets. So on Earth, we have the Heliostat on the ground, and then on the moon, we also have the Heliostat satellites. On the Earth, we will bring forward the constructible sun in an ecological way because we know that the demand is increasing. And then on the moon, we will be able to build all these bricks that will allow us to settle down for the astronauts and to build all the infrastructures that it's been planned by many agencies and many companies. And on the Earth, the strategy is short-term, but on the moon, it's actually mid-term. So you will see what happens. Next slide, please. Here you can see our team, our French team, and me, I'm Spanish actually. So I'm a bit of an intruder, but I'm studying in France. We have a bit of different backgrounds, which brings a perspective into this project. And yeah, now we need you to join us and to help us to bring this forward. Thank you so much.
Okay, are any questions?
So lunar regolith is like the miracle. Lunar regolith is like the miracle answer to construction on the moon. And then on the Earth, using the sinter process, you would use solar furnaces on the Earth or to do the sintering.
Yes, exactly. So we want to first prove the technology on Earth in order to gain money and experience, and then move to the moon when we have the money and we know that it works and it's feasible. Yeah, that's in the case because we know that also, like, not everywhere on the moon you have constant solar power. So with the satellites, we can use the power and then bring it back onto the solar center on the ground, on the lunar surface.
Well, I'm sorry to cut you short, but some people paid big money to have the lunch right
Yeah,
next
I get
door
it.
here.
Don't worry.
A wonderful presentation. We're going to collect all your surveys, and the judging will take place after the conference. Thank you very much, everybody.